So consider an elliptic curve E over some field K, and say you have an isogeny from elliptic curve to itself. So it's an endomorphism. And what we are trying to do is we take a point P on the elliptic curve E here and add it n times. And it so happens that after adding it n times, it gets mapped to the origin or the special point of the elliptic curve here. So this En, more formally you can write it as this point is on the elliptic curve. So this point is in the closure of the field, and this np gets mapped to the origin. So this En is called the n-torsion subgroup. So we are adding the point n times, so it is also called multiplication by n map. So let us see an example. So for characteristic of the underlying field not equal to 2, you can consider this curve. So this is an elliptic curve. So now we want to find the points 2p, that is, you add the point to itself, you land in the special point. So you get 2p equals to 0 if and only if y is equal to 0. So this special point is essentially 0, 1, 0. So this was shown in the lecture where we talked about the group law. But if you have already forgotten about it, that this adding the point to itself leads you to the point at infinity or the special point, you can see this on page 14 of Elliptic Curves by Washington. So there again this is shown. So in the book by Elliptic Curves by Washington on page 14, it is shown that for 2p equals to this special point, we have to have a vertical tangent line at that point. So that means y is 0. So for y is 0 for obviously all the three roots. And then if you homogenize this, then you will homogenize this, you will put a z here, you will put row 1 z here, row 2 z here, and row 3 z here. And then you can see you put this point 0, 1, 0. That will also satisfy this equation. So you have 4 points precisely for two-torsion. So this is two-torsion subgroup. So in general you have n-torsion subgroup. This is two-torsion subgroup, and this is iso 2 z by 2z direct sum with z by 2z, and this is the element you can say is 0, 0. Everything else you can give other elements. So say row 3 you can just give 0, 1. This you can give 1, 0. This you can give 1, 1. That doesn't really matter. So you can see the order is 4 here. So the order is 4. So luckily for us, if you define an elliptic curve like this, y square is equal to x cube plus ax plus b, again the characteristic of the underlying field is not 2, and say n is any positive number, positive integer, then np is given like this: some phi n over psi n square, then omega n over psi n cube. Now these are all special polynomials which are called division polynomials. And the fact which we are going to remember is that this endomorphism, so this endomorphism from E to E, so you're taking a point on this elliptic curve and adding it n times, so you will again land on the same elliptic curve, but this is a map from E to E, so it is an endomorphism. This has degree n square. So we can find these division polynomials on page 81, again Elliptic Curves by Washington. So this psi 0 is 1, psi 1 is 1, psi 2 is 2y, then you're given psi 3, psi 4, then you're given it recursively for odd psi and for even psi, and then phi m and omega m are defined. So all these you can find on page 81, and then here on the same page and around it, it is proven that this is an isogeny and the endomorphism of this is n square. So we are not going to prove this result that np is precisely given like this and the endomorphism degree is n square. You can see the book. So we are going to go further than this and prove the next result, that the order of this n-torsion subgroup, this is precisely kernel of times n map. So as we said that you add the point to itself n times, so this is nothing but kernel of times n, because you add the point to itself n times, you get to a special point on the curve. And so the order of this is n square now, because we are saying the endomorphism has a degree n square. And we have seen before that this will be a separable map. And so since it is a separable map, the order of the kernel is precisely equal to the degree of the isogeny. So order of the kernel is equal to degree of the isogeny, and that's why we can see the order of this n-torsion subgroup is n square. So we can do the prime factorization of n or n square, and then you can express this group of order n square as a direct sum of cyclic groups of prime order. So what we want to essentially do is we want to talk about all the primes which divide n, and then talk about what is their group structure for p times or l times. So we are going to talk about this. This is a prime L, and this prime L divides, say, n. And now we want to talk about the order of this group EL and its structure. How will it look like? So the theorem is this. So you're given an elliptic curve, and now you talk about L, which is a prime. Then E L to the E, where E is some positive integer, is Z by L E Z, direct sum by Z by L E Z, if L does not equal the characteristic of the underlying field K for the elliptic curve, because the elliptic curve is defined like this, E over K. And this is just Z over LZ or 0 if this prime is equal to the characteristic of K. So we are going to take this L as a prime, because once you know the structure for the prime, then you can do for any n, because you can say this n you can decompose as prime into its prime factors, and then put the cyclic group as the direct sum of these groups of prime order. So let us do this big theorem now. So let us first focus on this part. So say L is a prime and L is not equal to characteristic of the elliptic curve. So then times L map, that is you add the point L times, this is separable with degree L square. So we will have this. You will take the degree L square here instead of n square. So the order of the elements, this is a subgroup, so if you take 0 out of it, so the order of the elements is L. So you can write EL as Z over LZ, direct sum with Z over LZ, because the degree is L square. So that means the order of the kernel is L square. So if EL is a subgroup, then the order of this subgroup is L square. But each element which is non-zero has maximum order as L. So the only option left is this. We have obviously ruled out this option, because no element has more than L as the order. So this is it. So this is for the first part. So here E was 1. So E was 1. Now we take E as some positive integer. So say this ELE, this is generated by some points P1, P2, P3 all the way to PR. Each has order LEI. So P1 has order LE1, P2 has order LE2, PR has order LER, and then this EL will be generated by the same set of points, but now you just take one less. So LE1 minus 1 P1, then LE2 minus 1 P2, all the way to LER minus 1 PR. So then corresponding to these points, you have these points, and corresponding to them now you can have these groups generated, because this now has order L. So you have this corresponding to it. So corresponding to P2 you will have next one, corresponding to ER you have this. So you have R of them. So R of these. So therefore you write it as Z over LZ R. But now this we already know is 2 from here. You see R is 2 here. So this is the rank. So R is 2. So an important fact we want to notice is, and which we are going to use, is that for an abelian group G, this rank of GL, that is L is prime, so this L rank, so here in the L rank is 2, is same as the rank LE, where this is again L is prime. So L rank is same as LE rank. Now coming to this LE, so that is you're adding the point to itself L to the power of E times. So this contains elements of maximum order LE, and the order of this is L2E. So again the rank is 2, we know, because the this EL rank is 2, so here the rank also has to be 2, and we know that the order of the group is L2E and the maximum order is LE. So rank 2 is given, so therefore our only option is this. ELE is Z over LEZ, direct sum with Z over LEZ. You can see order is L2E and the rank is 2. So this portion is done now. So this first part is done. So now we come to the second part, where this prime is equal to characteristic of K. So if the prime is equal to the characteristic of K, it is no longer separable, it is inseparable, because once you start taking derivatives, then you will see that this will vanish everywhere. So now we have to prove that this is just Z over LEZ or 0. So say L is characteristic of K. As I said before, this you add the point to itself L times, L is a prime. This is inseparable. So the order of L, this order of EL, this is n-torsion subgroup, will be less than L square, because we have inseparability here. So if it was separable, you have equality. It is inseparable, so it has to be L square, because it's an inseparable map. You can split it up into separable and Frobenius map, and so because of the splitting here, you get less than L square. So instead of n square, you have less than L square. So case 1 is this EL is just, there is only 0 in here. So that would imply that ELE is also 0. So the 0 case is covered. This is easy. So case 1 is easy. So case 2 is, so EL is say Z over LZ. So because this E of order of our L-torsion subgroup is less than L square, so there are only two options. Either it is 0 or it has to be a divisor of L square. This L is prime, so the only divisor is L. So again this L we are talking about is prime. So only thing which divides L square is L. So that is the only case 2 we can have, because it's less than L square. So say it is generated by a single point P with the order of P as L. So because these are points, these are subgroups, and they are generated from points on the elliptic curve, so we are taking points. Now this isogeny by multiplication by L is surjective, so there is a point Q such that LQ is equal to P. So let us see this more in a diagram. So say this is our point P sitting right here, and then we have, you apply the isogeny L to it, and you have our special point O. So now this isogeny is always surjective. So say you again have elliptic curve E, so this is elliptic curve E, you have the same elliptic curve E, again you have this map L, or multiplication by L map. So this map is surjective, so we can find the inverse image of P and say it is Q. So now LQ is P, so you add Q to itself L times, you get P. So that is what we are saying, LQ is P. But then point Q has order L square, because first you multiply with L here and then you multiply with L here. So you can see L here and then L here, it gets mapped to the special point O. So we can iterate this procedure, and you can iterate it procedure to get a point in ELE of order LE. And since the rank is 1, so see the rank, L rank is 1 right here. So the rank is 1, this rank will be carried to L to the E. So we get EL to the E as Z, LE, Z. So let us now construct these points recursively to see them. So say now you can construct a point Q1 here. Again you have multiplication by L map. So L, L, L. So this Q1 will have order L cube. then again all these maps multiplication by L are isogenes and they are surjective. So you can find a Q2 here, and you have L, 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 L. So this Q2 has order L4. So these are the generators of this group here. And we said that EL is like this, and therefore this is like this, because rank here is 1 and rank here will be 1. So we are done.